Hi, my name is Vivian and I was in charge of animating. While this video is like a brief making of, I hope it will serve you as a tutorial for animating yourselves because it's really fun once you get the hang of it. So I'll start off with the cellular view, and then later on we'll move on to the molecular view of our animation. I won't go into too much depth about like the basics of polygon modeling and stuff, but I'll give you a brief overview of how these cells are actually composed. So what I did is I built the cell from different polygon objects. So polygons are these here, and you can assemble them into different shapes. So I had a nucleus, different layers of the ER, a cell membrane, and the mitochondria. So for materials means like the color and the texture that you assign to an object is a simple brown for the nucleus, ER, and mitochondria. I'll just quickly show you what the cell membrane looks like because that's actually an animated texture. So I'll open the hypershade here, which is the window you use for composing materials and textures. And I'll move to the cell membrane here. And this network here is actually what my cell membrane is all about. So you can see this in the preview here. And my basic output material is actually this fawn material. So I have like a light blue color, almost all transparent. And like I adapted the cosine power to this value to make them like shiny as like I wanted them to. So if you see, you can make them shinier or less shiny depending on what you want. And this is really important to make the cells look organic, is the ray trace options. So you want to make sure that you check refractions and give it a refractive index that's not 1. So what this actually does is it simulates light passing through like a phase boundary. Like if light goes from air into water, you will see the refraction. And this is what Maya then actually simulates. It costs a bit of like calculating time to actually do this in rendering, but this makes for a really cool look. So I'll just quickly close this here, and just a note of caution: if you do this refraction, you want to make sure that you have the mental renderer selected, because otherwise the refractions won't actually be calculated correctly. I won't actually show you what the rendering looks like because one frame in this particular animation here takes like 5 to 7 minutes to render because of the refractions. But you can all look at the end product, which is actually rendered out. It took me like a day. Alright, so now that we understand our cell models here, I'll just show you what my actual models here look like. So when I go into one group here, you'll actually see that I don't have this group here anymore. I actually have a single mesh object composed of all of these. And this is actually useful if you don't need to access the single polygon objects anymore. And the way you do this is you select all of these, make sure you are in the modeling tab here, go to mesh and combine, and this will actually give you a single polygon object composed of all of these here. Alright, so you may have seen that what this animation is actually all about is the cells first fluctuating and then aggregating into a pile. So of course I did not code the trajectory of every single cell because that would take a lot of time, would probably not look that natural. What I actually did is I made use of Maya's physics. So Maya can actually calculate physical parameters of an environment, and what I did with the cells is what you call rigid body physics. And the past lysine, which is this here, what you see down here, is particle physics. Okay, before we go into the more complex details of this particular file, I'll just quickly show you in a new file how this works. So I'll create a sphere, and I'll create another sphere and scale this up. And I'll hit X-ray here so that I can see inside here, and I often do this shaded wireframe mode because I can then see this better. Okay, then I'll open the outliner here so I can select these. And what I'll do now is make sure you have the FX menu open. Then you go to Field Solvers, and then you create an active rigid body. Then I select this here, and I create a passive rigid body. And I want this one here to fluctuate within the boundaries of the slaughter sphere that I created. And I do this by using a turbulence field. There are several different parameters that you can actually code here. The most important ones is the magnitude, which is how strong it is, and the frequency, meaning how strongly it fluctuates with time. Okay, so let's just see what this does. And now we see that it doesn't really do anything yet. The thing is, I'm not really sure why, but sometimes Maya will have problems like recognizing this as a passive rigid body the first time around, so sometimes it helps to just delete the rigid body here and assign it new. And actually, I'm going to try something else here, which is sometimes necessary, is the reverse. You know, still doesn't do anything. Just quickly delete all of this here and assign this again. And I'll have to assign the turbulence field again actually. I'll just select both of these and go to assign to selected, which will then assign my sphere to the turbulence field. Okay, so now it works. So I'm not really sure why Maya does this sometimes, but it always helps, like if something doesn't work, either like delete and try again, or sometimes it also helps to close the file and open it again. I'll just actually crank up the playback range so we can see this a bit better. So now you see that this cell object actually stays within the confines of this outer sphere. So to repeat, what I actually do is I make the object I want to move an active rigid body, and the object I wanted to collide with a passive rigid body, and I control my active rigid body using different force fields here. And this force fields is actually what the physics is all about. Alright. Then I'll just quickly show you how the particles work. I'll just delete my cell here, and basically this is pretty much the same way I did for the past lysine, is you go to N particles and go to fill object. And now this will fill your object with particles, and it will create an N particle object here and a nucleus, and this nucleus is actually the item that calculates the trajectories of these particles. So now if we actually hit play here, you will see that the particles just fall down. The reason for this is because a nucleus, if it is created new, has a standard gravity encoded here. So if we don't want our particles to just fall straight to the floor, we need to go to 0. And now the particles won't do anything much because now there's no force. So basically I also want them to fluctuate, so I just go with the very same thing. I go with the turbulence field that I apply to my particles. And now you see that they don't stay in the confines of the sphere. Because we still forgot to do something, is now this rigid body won't actually help here anymore. We have to make this a collider, which is somewhat confusingly in this N-cloth menu. You go to create passive collider here. And now these particles actually stay within the confines of this outer sphere mostly, so sometimes one particle or other will actually slip through. But yeah, so this is actually the two basic physics that I use for animating the cells. And I will just go back to my actual file. And take a look at a couple of special things here. Alright, so what I actually did the first time around was take these cell meshes composed of like all these different sub-meshes and make these a rigid body, which resulted in the animation like playing back really slowly, because it kind of like calculates with all the internal faces even though they're not relevant at all to what the active rigid body is actually supposed to be doing. So if you have a complex object with a simple surface that you want to animate, you want to consider using a proxy object for this. This is what this cube here is all about. So you see this is actually on the surface, and here I only have my mesh, and if I go to the P cube here, you will see that the rigid body is within the P cube. So not my cell is the actual rigid body, but the cube. So the trick here is just to make the cell object actually follow the other. And I'll just quickly duplicate this here so that we can look at this. Right. Okay, I'll just delete this here. I'll come back to that, why I had to delete this. And I can also delete the rigid body for the time being. So now I only have my mesh and my proxy object to be in this group. And now I just take the group and move this over here. Like, be sure to select both of them. Alright. So now in this group here, I can actually select the cell and move it independently, and I can select the cube. This is actually a smooth cube, and move this one independently. So how do I get the cell to actually follow the proxy object? So what I want to do is I select the object and I go to modeling here and I create a deformer and I create a wrap. So let's see if this worked. Yes. So now you see that I have only the cube selected, but the cell moves with the cube. This creates this one here. This is just encoding this wrap deformer. And now I can actually go ahead and make this P cube an active rigid body with here, create active rigid body, and then assign it to a field, which is basically what I did with all these cells here. So I'll just quickly delete this one here. Okay, so far I only talked about turbulence fields. Just to quickly explain how I made the cells aggregate, you need a different type of field, which is a radial field. So you have this magnitude option. So if a radial field has a negative magnitude, it draws objects towards its center. If the magnitude is positive, then it will like repel the objects away from a center. So I actually use the negative magnitude here. So you see at some point the magnitude decreases to -1, so that the cells start to move toward each other. Okay, so I'll quickly just go into the rendering type here of my particles actually, because the standard rendering type is like just points, and in a complex animation these points won't really be visible. So you have this shading tab here, and you want to go with the spheres, because here you can actually determine the particle size. So if you look, I go up with the radius and my particles will get larger. And so it was a bit of trial and error to find like a radius that suited me. So you can just play around with that. And the color is actually coded here. And now to make these particles not penetrate my cells, we basically go with like the same approach as with the boundary sphere that I showed you before. And this is like going to encloth and creating a passive collider out of each of these cells, and then the particles will actually collide with the surface of the proxy object if I make the proxy object the passive collider, which I recommend. Okay, so still, if you have a fairly long animation, which is also fairly complex, which is useful to know, is that you can actually make the program not evaluate the physics, which is good if you need to manually like key in your animation, which is going to modify evaluate nodes and you ignore all, and then it won't actually do anything anymore. So if I hit ignore all, you will see that, come on. Okay, kind of like, yeah, now it's all off. And now you see that the cells don't move, and the particles don't move either. And this is helpful, for instance, I'm at some point actually key an upward movement of this whole object here so that the particles then move into view to the cells. This is what these red lines are all about. So you see that you have this movement of this object between these red lines. And this is easier to actually key if the program does not have to calculate these dynamics between these different frames. Okay, so this is basically the fundamentals of the cellular animation. So we'll just go ahead and open the next scene, which is the molecular view, which is here. Which will probably take a bit to open because that's fairly complex, really. Okay, so there we are. And the first thing I'll do is actually make this membrane object, which is this yellow stuff here, invisible, because this takes really a lot of calculating power to have live in the viewport here. So I'll just go off, switch the perspective camera, and so now we can actually rotate this pretty freely. And for us to still visualize the membrane, I'll actually make this plane here visible, which is actually what codes the motion of the membrane, which I'll come to in a bit. So I'll just start off with how I actually animated these or modeled these receptors, and then I'll go into the motion a bit. So I'll just quickly open a new scene to show you how the molecular Maya plugin works, because that's what you need to actually import real protein structures. So there's actually a whole site about this tutorial, this plugin, which is molecularmovies.org. At least it's pretty much concerned with animating and modeling proteins in Maya. And there's actually this toolkit here where you also have a couple of tutorials which are pretty good. And you also have these tutorials which are also pretty neat. So actually this is the tutorial I used for animating the membrane later. Okay, so you have this option here, PDB import, and you can type the PDB code in here. So I'll just go with this one. And you can import post download. Then you hit download, it will download this from the internet and then actually import the protein structure here. So this is stripped evident. as you see, tetrameric has 4 chains. And this will now create a nucleus object here and a group with these chains in here. And in this attribute editor, you can actually display different view modes of this. So this is the atomic view, the space filling one. But for our animation, we actually want the surface. So by default, if you go to mesh visibility in the surface tab, it will give you this like really, really rough and coarse structure. So we want to go down with the resolution a bit. And now this will kind of like look a bit edgy sometimes. So we'll just select this again and go up with the smooths. I usually had 10 by default, and it makes this whole thing look a bit smoother. So by default, Maya just gives all like each single one of these different chains I think random color. So this is how these colors actually come to be, but we can easily change them later. All right. So this is how we actually get the protein structure into your file. So one problem I had early on is that you can't delete these. You see, you have this error message here, cannot delete locked node. And it took me a while to actually get behind what this means and how to actually circumvent this. So what you have here is this mel, which is a scripting line, and there's actually a command to unlock this, which I'll just quickly show you here up on the big screen with a larger font. It's lock node space lock space off, and then the name of the node, which is here, it's pdb mol struct underline 3wyp underline 1. And this is what I'll type in the mel scripting line now. Okay, and now the miracle happens, I can delete this. And so this is actually really helpful to know if you don't want to like either have like accumulate like tons of different protein structures in one file, because if you want to select one, or like I did at the beginning, deleting every single file if you imported the wrong protein. All right. So the second thing I actually had to deal with is I only need the surface here for my animation. So this is actually like, I don't actually need the background info here. So this is probably a dirty way to extract the polygon meshes from this object here. But what actually works is if you have unlocked the node, then you just create any sort of polygon object. It doesn't matter which. And then I'll just go ahead and select these chains together with the object I just created. Then go to edit and group. And now in this group, I will have these chains now extracted from this node here. And now I can actually see these meshes here. So now I'll just go ahead and select these and pull them out, and then I can delete these entire things. This will now turn green, but this is only because I now deleted the material here. So I'll just go ahead and assign the standard Lambert for the time being. And then we have our strapped evidence structure. And now it's really only the mesh. And if I want, I can also like group this and call this group strap Davidin. And now I can work with this really well. So the way I actually built the membrane proteins I just showed you is by looking for the N and C terminus in the PDB file and just like positioning them together. So this is not maybe like, this is not an entire structure of like that the actual membrane proteins sequence is coded here. This is just like manually built together. And then grouped. Okay, so here you actually see the stripped evidence with the different materials. And basically I just like took mRuby, EGFR transmembrane domain, and then the different extracellular domains. And I actually created this biotin molecule myself from like small spheres, as you can see. But that's accurate enough for our purposes. Alright, so I'll just quickly show you how the membrane motion actually works, because that's pretty neat. So I'll just make this plane visible here, and let's see in the playback. You can see that this actually makes waves. And the reason why it does that is because this is what you call an N-cloth object. So if you remember, we had the N-cloth menu object to create this passive collider, but you can also create an N-cloth from something. And this will actually make this look like an actual piece of fabric. And this is actually explained really, really well in this tutorial here, so I can only recommend this. But basically what you do is you make this plane an N-cloth object, and then you apply a turbulence field, and this turbulence field is what actually will make the membrane move. I did just one tweak here, which you can see with these lines, is that I actually fixed the N-cloth object here, because this is where my membrane proteins are, and I don't want the membrane to like move excessively up and down here, because I don't want to like have to code my receptors moving up and down with the membrane here. So let's just see which one was my constraint. I'll just have to like quickly look. Okay, this is actually, this is also a different kind of constraint here. I'll just quickly make this one visible. So this membrane is actually fixed in place by these constraints here at the outer rim, because otherwise the membrane would just like crumple up and fly away. But you can think of this as tethers. So this membrane is fixed here with these lines, and it cannot actually move away. So, and this is actually the dynamic constraint I had here, and I basically just coded another plane and then made this dynamic constraint. So maybe just let's take this away, and let's see what our membrane does now. So you see now it moves like a lot also here, which is maybe not so good, because the membrane should actually stay around this transmembrane domain. So how you actually apply this constraint is I select my constraining object here, I'll select my membrane here, my N-cloth, and I'll go to vertex mode for both of these, because I actually make the constraints between the vertices here. And then I'll just quickly move to the top view, so this becomes easier to select. And if I draw here, okay, now you can see we can actually select the vertices on one of these objects. Oh, not this. actually it makes sense to go to components and then just say vertex, because otherwise I can also select other objects, which is really a pain. And alright, so in this mode I can now make sure that you have like the vertices of the constraining object selected, as well as all the vertices in the vicinity of the enclosed object. And now I can go back to perspective, and then we go to end constraint and go component to component, and this creates this constraint here. And now this is exactly like it was before, so you see it's fixed. Alright. So now I'll just quickly go into how I actually made these receptors fluctuate, because this is actually not an instance of rigid body motion, and this is actually something I coded myself. So this is actually a handy gadget here. Here, this is my receptor, and you'll see that these three are purple. And I'll just quickly go to a different file, a new file, and show you how this works. Alright, so I'll just create a cube object here. And then I'll just quickly show you how this coding works. So what you can do is you click on here and go to create new expression. And then you get this editor here, and here you can actually type something. So for instance, we would go with something like p cube 1 dot translate x equals, let's just say noise time. Noise is a noise function and time is the parameter. So it will actually, this value will now fluctuate with time, because time is now a parameter for this. Now I create this, and now you can see that this actually moves here, because now this is actually controlled by this noise function. And I can do the very same thing with all these other things, and what I actually did for the receptors is I coded the movement in X and Z directions, so like a little bit into the membrane and from left to right, as well as the Y rotation, so that it rotates around its own axis. So let's just have a quick look at this here. You can actually also go with like conditionals like I did here, because I explained different types of membrane proteins here, and I only want the membrane protein to move when I'm talking about it later. So with these conditions here, I can make the EMA receptor actually move if until frame 270. I can actually make it freeze until frame 270. So this is like translate x equals 0. And then above frame 270, I give it this noise function. So then until frame 270 it will just stand still, and above it it will start to move. Okay. Then let's just quickly go on to how I actually animated this past lysine. So you see, this is actually not just that the whole object like rotates, but it has this internal flexibility, and this is actually pretty neat. So I'll just open a new scene, and quickly show you how to do this. Alright, so I need a Maya for this, and I need to import this one here. This is actually not a file taken from the protein data bank. This is a file coded by someone at our department with a program called Cube. So many thanks again for this. And so now we have this molecule here. And I'll just quickly go ahead and extract the mesh here like I did before. Might take a while, yeah, alright. Okay, so then I'll just go ahead and create a sphere, unlock the node. ref1, and then actually I still have to make the atoms invisible. Select the chain, select my sphere, group, and then I'll extract my mesh here. Alright, so then I'll quickly go ahead and actually delete this one here and make this align a bit with the axis, so like this, and like this. Okay, so it's like fairly aligned. Right. Okay, what I'm going to do now is I'll rig this model. Rigging is actually the action of placing a skeleton-like object through a mesh to control said mesh with this. So this is this rigging here, and this is create joints. And the important thing is once you rig an object, you cannot move the mesh around anymore. You will have to move your mesh by the parent joint. And because in our animation I had the biotin that bound to the EMA receptor somewhere in the middle, so this is actually the point that I needed to control translationally throughout space, and the rest could fluctuate. So I placed the parent joint here, which is now invisible behind this object here, but we can actually, I'll quickly scale this down first because we do not need this to be so big. And then it'll be more visible. Okay, so now we have the smaller object, select the joints again, and now you can see that it places something here. Now we can just go along and place joints at strategic positions along the past lysine here. And actually you can think of like these triangles being the bones and these spheres here being the joints. So these joints are where the mesh will later be able to bend around. Okay, so but now if I have this joint chain and I do something to one joint, actually I'll still have to place this on the object. Just move this up real quick, like so. Okay, so, but we might now expect to like see something here, but now if I try rotating but nothing happens. The chain rotates, but the mesh stayed where it is because we forgot to actually skin this, meaning to tell Maya that it should use this joint chain to actually deform the mesh. And this is this button here, it's bind skin. And once we have this, now we can actually control this. So you see that this here also moves with the joint chain. The reason for this is that it actually binds the entire mesh to this joint chain, which I only put through a part of the mesh object. In my real animation, I actually had a second joint chain starting here, extending outwards. And then this artifact also goes away. So, right. So my first trial was actually coding each joint with expressions for the rotation here. So you can also create noise expressions, but the problem is that's fairly hard to control because it might sometimes dip into the membrane or like cut another protein and stuff like that, and that's not nice if that happens. So what I actually did is go with a further level of control, which is an IK spline handle. So we go to the rigging menu, go to skeleton, go to create IK spline handle. We can just hit the options here, but this is pretty much this works. And now we click on the second joint. You don't want to click on the parent joint because otherwise you won't be able to move the mesh like up and down independently anymore. So we click on this one and we click on the end joint, and now you can see that Maya actually created a curve here. This is the IK handle and the curve is here. And this curve is now what we want to actually modify this thing here. So we'll just quickly go to select control vertices and let's see what happens. So here you can actually rotate them, you have to move them, and now you will see that the joint chain follows the motion of the curve. You can go here. I could also like take this one and move it here. And this makes for a much more organic movement, and with these control vertices, and I can also control this more precisely so that it does not penetrate the membrane or other proteins. So now that we understand how this process works, let's quickly go back to our actual file here. And here, here you can see that I have this curve here. This is this here. That these are these curves that I showed you just a minute ago. So here are the curves. And the way that you code this is actually, the way I did it is every 15 frames I kind of like chose a new shape of this curve. And to animate this, you want to go to the channel box here, and with control vertices selected, you can go to CVs, click to show, and then it shows you the coordinates of each of these points here. And if you select all these and then hit key selected, then this will actually fix these coordinates for this frame in which you fix this. So here you see all these red lines is where I actually defined a new shape of this curve. And this is then, that's the way it moves. All right. Okay, so how I actually did this binding approach here is, as I told you before, you should not parent the curve to the actual parent joint, which is joint 1 for one part and joint 14 for the other half. So I'll just quickly make this one visible here on. So you see that this chain is like for the left part, so the other one will be for the right. And the advantage is here that when I select these two parent joints and hit W to move this, the entire object moves. And this is actually how I did the binding. Before I actually modeled the fluctuation, I had it move from somewhere up here down into the binding pocket. So for binding, you want to first go to the frame where you want it to bind. So in this case it's frame 270. And then you, in this frame, you position it the way you like and take care that the membrane receptor's fluctuation is already programmed. And then in this frame you will key the position of this fluctuating object here with the translate here. So you see this is keyed, this is where it's red. And then you move backwards. So you say, okay, now it moves upward. You see how the translate values and the rotate values actually change. And then you go with actually the fluctuation, because then you already have like the macroscopic motion here, and then you can take care that this past lysine doesn't dip into the membrane or anything. Okay, so let's just quickly have a look at how the streptavidin molecule works. Where is it? It's in this group here. So here I coded X and Y rotation, and much the same thing I first coded like the binding event in the one frame, and then I actually coded this entire thing here. And what I forgot to mention until now is how do I actually, after binding, make the objects stay together. So how I do this is that these two objects, this past lysine, or actually it's joints because I don't actually move the past lysine anymore, and the EMA membrane protein are in one group. And this is where we saw the conditionals before. We go to edit expression. So this receptor alone will fluctuate until frame 270. And this takes over from frame 270, so you see below frame 270 the translation of the group containing the joints that control the past lysine and the membrane protein itself is 0. And after that, the individual fluctuation of the receptor here becomes 0, but then the entire group takes over for the fluctuation, so it looks like it binds and then it just keeps on fluctuating, because then it's in fact the entire group that does the motion, not just the receptor itself anymore. And that's the way they easily stay attached. Okay, then just one final thing. As you may have noticed, the receptors I'm currently not talking about fade out if I don't talk about them. And I actually coded this a bit so that I can actually access this here in the file without having to go to each single material and go to transparency and change this. Because this is technically the first thing that comes to mind is you assign like a specific material to each of these objects, and then you like change the transparency manually for each of them, which is a bit cumbersome. So this is where Hypershade comes into play again, because I actually defined 3 transparency controls. So I have like this one, the EMA trans, and I actually map this to every object that is in this group that I then want to fade out together. So both components of my past lysine and all my components of the EMA membrane protein. So what you do here is you output the transparency and input it into transparency, meaning that I cannot individually control the transparency of this material, which is why this is grayed out. But I now control the transparency of all these with just the transparency in this single material. And to access this here is I built like 3 cubes, which you can see there at the side, just so that I can actually have the object that carries this material here. And so if I want to now change the transparency of this entire receptor here, for instance, the BAP, then I just go like here and I change the slider. So this won't actually show up in the viewport here, but it then shows up in the render. So I don't have to like click on every material and code this separately. Okay, so this was mostly it. So I hope you learned something, I hope you enjoyed it, and I hope that maybe you will do some great animations yourself someday.